Hello, my name is Surya Sundaram and this is Lab 5 for Physics 2212, Faraday's Law. So the purpose of this lab was to explore why a falling magnet through a non-ferrous tube would be different than just a free fall. So we will relate the magnetic field of a falling magnet with time to a Curly electric field around the non-ferrous tube. We will see that this will create a current which will create a magnetic field opposing the direction the magnet is actually falling, and this kind of deals with Lenz's law and Faraday's law as well. So for Faraday's law, this is when the magnetic flux linking a circuit changes, an electromotive force, or EMF, is induced in the circuit proportional to the rate of change of the flux. So we also use Newton's third and second law. Newton's third law is the force an object exerts on another object is equal and opposite to the force exerted by the second object on the first object. Newton's second law states that the acceleration of an object is dependent on the force on an object and the mass of that object. The Biot-Savart law is also used because we are using a magnet, and this describes the magnetic field created by a current carrying wire. And finally, Lenz's law is dropping a magnet through a non-ferrous tube induces an electric field which generates a magnetic field in the opposite direction that the magnet is falling. So the procedure was to get a roll of aluminum foil, a bar magnet, and our smartphone, and a tool for measuring the dimensions of the tube. After we found the magnetic north of the magnet, we marked the north pole of the magnet and then filmed ourselves dropping the magnet through the tube, and using this footage we calculated the time it took to actually fall through the tube by looking at the different time steps. So the data and measurements. So the measurements, the tube length was 0.306 meters. The foil width was 0.012 meters. The inner radius of the tube was 0.023 meters, and mu from lab 3 was 1.737, which we will use in our code. So through 5 trials of dropping it through the tube and looking at the timestamps, the average of these times was 1.37 seconds. So now on to the actual coding part. So as you can see, we first initialized our constants and then initialized our graph, and we created the tube of aluminum foil using the length, width, and radius that we measured earlier. And then we defined the magnetic field function and the magnetic flux function from this field function. So after finishing the rest of the code, I got that the time to fall through the tube based on this computational model was 0.951 seconds. So on the left you can see the model of the magnet actually falling through the tube and the magnetic field generated by this, and on the right you can see how the velocity changed over time throughout the 9.9 seconds. So for the conclusion questions, so what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So the magnet would fall at a slower constant speed because of the magnitude of the upward magnetic force would increase. So what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So if this was done, there would be less magnetic force from each ring along the non-ferrous tube, so the magnet would actually fall faster because of this. So why can't you do this experiment with a ferrous tube? So the reason we use a non-ferrous tube is because the magnet would have a force from the magnetic field between it and the tube. The magnet will actually stick to the sides. So now looking at the reasonability of our computational model, so between the model and the experiment, there was a 0.419 second difference, so this is a 30.6% error. So